Alright, so let me start at the top for you guys, okay? And then I can scroll back down as we explain, so you guys can keep engaging and adding some extra details. So this big picture is, when we're looking at the entire molecule after we've drawn the structure, and we've kind of said, okay, here's where most of the electrons are, and according with bond polarity, and this is its shape, we should be able to get a general understanding of, is there equal or unequal distribution of charge across the whole shebang, across the whole molecule. That's really what the big picture is here. But sometimes it's a little hard to figure out on our drawings, so building them helps, looking at them in kind of a different way helps, so we have to kind of go along with these rules. Generally, if you have bonds that are nonpolar covalent, overall, generally the molecule cannot be polar. I'm not going to put a star there, because this is very much a general rule that we'll kind of go along with. So if I have a molecule, I'm just going to draw circles. If I have a molecule, so look over here too, okay? And I have a bond here and a bond here. And this bond over here is nonpolar covalent. Nonpolar covalent. By the way, how am I figuring out if something is nonpolar covalent? Well, I would have to draw the arrow if it's polar covalent. What am I looking for? Electronegativity guy. So this electronegativity guy is approximately the same as this, and is approximately the same as this, because there's no difference in pull for electron. I would have to say overall this molecule is nonpolar as a whole molecule. But the reason why is because there should be an equal distribution of electrons on this bond here, which gives us the opportunity to say everything is equally distributed, and equal distribution generally is going to be nonpolar. Now, how have I drawn this shape, this geometry? I've drawn it linear, right? Sometimes we'll have things that are bent, like this, because there's lone pairs, and they'll still be nonpolar covalent bonds and nonpolar covalent bonds. And so then you're like, is it really nonpolar and low? That's the hard part, because these lone pairs up here are certainly giving the top region what kind of charge? Lone pairs of what again? Electrons, right? So what do the lone pairs of electrons kind of carry along with them in terms of charge? Negative. So this is certainly partially negative up there. And this lack of electrons down here might give us the opportunity to say this is polar. But that's why this asterisk is here, because it is a generalization. Now, if we have polar bonds, we have to defer to the shape to figure out if that situation overall is going to be polar or nonpolar. So I'm going along with my same image here, and instead of putting nonpolar covalent, I'm just going to put polar covalent. And so if I have a polar covalent bond, what should I be drawing along with that? What's the arrow called? Dipole moment, okay? So I don't have the atoms indicated here, but I'm just going to tell you that this molecule over here has a higher electronegativity. That's real bright. It's like her bound bright. Okay. It's got a. What's that other orange marker? Oh, here it is. Okay. This one over here has the highest electronegativity of them all. So I'm going to draw an arrow pointing towards this atom X, and I'm showing the dipole pointing that way. So what kind of charge do I feel over here? Partial negative, right? So if I tell you that this one also is compared to, I'm going to put A, B here. Okay. So A is less electronegative than B. Where would I draw my arrow between A and B? So the same direction towards B, right? So if I said A is less electronegative than B, I'm going to draw my arrow. I'm just going to draw a little arrow this time, though, because maybe it's just not quite the magnitude of difference that these two had. So A to B is a polar covalent bond, B to C is a polar covalent bond, but B to X is a polar covalent bond. B to X is just more polar just because its electronegativity difference is higher. So overall, I've drawn partial negative on that side. What would you guys draw on this side? Okay, so partial positive. So the shape that I have here, linear shape, does it allow for me to cancel out the dipole moments? Yay or nay? It's just make a choice. You guys are squinting at me.
No.
Okay, squinting at me means no. You're like, no, I'm not sure. A little skeptical of that, right? It's not, because both arrows are pointing that way. So all the electrons are pushed this way, and there's very few electrons over here. So we definitely have what kind of molecule here? Polar, because it's not unequal distribution of charge across the entire shebang, the whole molecule. Okay. Now I'm going to keep my shape here as linear. What if I have polar covalent bond and a polar covalent bond. Okay, gonna keep that stuff there. And let's say I had A, B, A added to, or bonded to each other in a linear situation. And B to A was super, super polar. B to A is also polar over here, but how's the arrow pointing this way? Towards the A, because I'm telling you that A is more electronegative, meaning this A, again, I'm just identifying those by letters in the same atom. They're also electronegative. So I've got the same arrows, opposite directions. So what's the kind of field charge over here? Partial negative over here. Partial negative. Okay. So would you guys say there's an equal or an unequal distribution of charge there? Equal. Equal. So then overall we would say this is a non-polar molecule because I have distributed the charge equally across the entire landscape, the entire molecule. Yes, ma'am.
Okay, so I get how to like do it, but I don't know what any of it is.
So the reason we have to figure out our polarity stuff is actually something we're going to talk about maybe in like half an hour to an hour. Is it once I figure out if a molecule is polar, it tells me every property that it can have and like what does it do in the real world. So once I can figure out if something is polar or non-polar, I can then say, okay, well, water's polar. Like most people kind of maybe heard that before, water's polar. Well, why can water interact with like salts and other kind of solvents, but not oil? Why can't it interact with oil? Because oil is non-polar, right? We say, oh, their densities don't mix and it's lighter. One's hydrophilic, one's hydrophobic. But there's reasons why we're figuring this out now, so we can actually talk candidly about the problems later. Does that help, Izzy?
Yeah, kind of.
It's just like the reasoning behind it. But so yeah, we have to do this first to get a deeper understanding here. Okay. So I said that this could cancel because it was linear. But what if I had drawn it like this one up here? And I had my A, look up here, stop talking to your neighbor, you move that down in a second. And I had my ABA situation here with me. Where are my arrows pointing in this drawing? To the A's, down and down. Okay? Because I'm telling you the situation still remains. They just have higher electronegativity. I've drawn this one in a linear fashion. You guys said it could stretch this way and push the electrons out to left and right, equal on left and right, non-polar overall. What about the way this one's drawn? Well, the top also has, would you say, a pole or a pool? So it technically kind of does because those lone pairs are there, but those are a different magnitude of charge. Okay, they're different magnitude of the electronegativity. So this one over here might be a little teeny electronegativity difference, so it's going to be a little partial negative. This one might be a little partial negative, and this one up here might be like a super, super, super big. I'm going to put like tons of partial negative. So you have basically, yeah, it's negative everywhere, but it's not the same value of negative. So we would then say that was a polar situation. But I'm going to flip those arrows around. Actually, that's kind of a hard example. I'm going to do it the other way, this way. And I left myself in that situation for a minute. Okay. What about this way? What's down here? What's down with the A's? Partial positives. And what's up here at the B with the Mickey Mouse ears? Partial negative, because the arrows are pointing towards it. It's a very large partial negative because both arrows are pointing up. So we have a region of partial negative on top, partial positive down here. So overall, would you guys say this is equal or unequal distribution of charge? Unequal, so then it's going to be polar. I know it's weird because it is non-polar is an equal distribution, not equal is a polar situation. Yeah, and with that terminology. Okay. All right, so we're going to need to practice with this a lot more in our lab. Okay. And here we go. Oh, I have to show you my comics first. Okay. It says, "Help! Help! I'm dissolving. The bears are insoluble." That's easy for you to say. You're not polar.
It's a non-polar bear.
Because that's a non-polar bear and that's a polar bear. And water is polar because of unequal distribution of charge.
That's so funny.
You guys all looked at each other like, was that supposed to be funny? Okay. It was. All right, so you guys have your drawings. I'm going to come around like a crazy lady, checking drawings and helping you out, but I got 30-ish of you guys, one of me, so I can't duplicate myself. But you guys can work with, I'll let you guys work with a partner that you choose. unless that goes poorly, and then we'll switch. But as you look at the person, listen, you have to compare your structures first and go through and like say octet, octet. Okay, this one's expanded octet. Can it? Kind of make sure your structures are drawn correctly first, and then you can build. But only build maybe 3 or 4 at a time, because I'm slow and I'm going to be working with everybody else, and you don't want to be out of stance or running out of things to build with if I'm the person holding you up. Okay, I have to check them off. That means that they have to be all the way completed through the 5th column. Okay, they're completed to the 5th column. So yeah, you'll basically have gone through electron dot structure, molecular shape, molecular polarity, and lone pair, because you have seen that. You can actually have your drawings correct. So go through the ones you know first, and then I'll kind of rotate around. You guys need to go back. Who wants to be my partner? You can work with one other person. One other person.
The test scriptions, are we supposed to do those at home, like finish them at home?
The unit 2 ones?
Yeah.
As much as you can.
Okay, were we supposed to take a picture of the last? Okay, because how do we do it?
You can't do the multiple choice. That's why I have multiple choice mostly in class.
Okay.
Finish your first ones on your own at home, and then I'll give you guys more time. If not, I'll just give you the credit.
Okay, thank you. Yeah,
Okay.
sorry, I was like,
You're good. I might need to tell that to the class. Yes, yeah, no, that's compare your structures first. Compare your structures first.
Yeah, I had no idea what to do. Well, because like the way my professor was doing this is she was saying there was an ionic bond, not a covalent bond. So when you do that, you can we'll do the dot structure the same. So that's how I got that. And I would think that it would be, you know, it's not covalent, so I'm not sure what that. Yeah, I didn't know how to do that. I kind of like left it. I'll ask her about specifically. I feel like I got a lot of these wrong, but I feel like I did this part right. This one, I don't think I did this. I think that makes me I don't know. I did good. I felt like but I didn't know. On a lot of things, like how do you know when to put, like how do you know when to use the triple lines and when to just do it, is what I'm confused about. Because that's right, but you could also do double lines here and here. And so that's where I'm confused. I'm not sure when to use what. Yeah. And then this one is I actually got it. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and there's 6.
Oh, see, that's where I did wrong. I got
That one makes sense way better.
yeah.
That one I probably want to make better.
See, I was confused. Like, it only had two, like X2.
Yeah, that's where I'm having a little bit of difficulty as well. I have quiz, but
Wouldn't there only be two X's?
you are right. I didn't even notice that. That's incorrect. So that means we have to change the where's us?
Yeah, I did 6, but I didn't have the X's.
Alright, so yeah, then it should look like this. That means that it's not tetrahedral, that means that it's I probably messed up a few doing the same thing. Okay, the next one is
That's what I got.
what about what you think?
Okay, honestly, I don't really know. I have no idea what I'm doing. I just kind of stuck in myself. That was like why I didn't know what I'm doing.
Yeah, because the reason why I was confused is because I didn't have this whole thing. Mine did, for some reason, my code doesn't have as many ligands as this one. See, that's why. Alright, so that one, this is it would be a trigonal 5 pyramidal because I was so confused, I was like,
Now, how do you draw this like this? Because I can just
for which one I can see you have 4. So what you do is because you've got 3 elements, right? XC, because XC is the first one that doesn't have a substitute. Use that one as the middle one. Each time I think we've been using the other one. I mean the very first one without the substitute as the middle. Like on this one right here. The first one is a subscript, so you don't use that one for the middle. Out the subscript. So, for this one, so you put X in the middle, and then you have to surround it by X. And there are 4. So you only put 1
sometimes like I didn't
for that. Right. I do at this time. I said that I just need to make sure that I was like doing it right. But the only thing that's complete about is that the things didn't add up. So I might just be wrong with this one. So I'm sorry. Because if you add up all of the dots and the lines add to 42, it adds up to.
Remember how it's like as in different
Yeah.
yeah, I counted it right because mine counted up to 42. Because four of 8 equals 32. And then you add 1 to 3.
I still got Four times 3 is what? 4 times 3 is 12.
So if you count the arrow itself, 4 times 8 is 32, right? And then if you add 8 and then the arrow points towards it. So it's the same picture.
I got 42. You got 42?
No, I got 40.
Okay.
I really thought I had
So that's why I did the second line. Because I wasn't sure how I was doing it. I was like 42. So I did the second line that's off. But I don't know, you might be able to do like 2 lines above the XP. And I feel like either one. I don't know. That's why I'm doing that. Because I can't tell. About that because where I kept on getting lost in this entire game. And so that's why I was
like, wait, because then she said it needed to be even. You know, well, that wouldn't be even if I did the line. It's not the low right here.
I had a low number of 5, so I guess it's I'm so confused. I'm so hard to understand. I'm trying so hard to get it.
And below. So everything below that expands on head. And I didn't even know what that meant.
No, I don't think we have any questions like that. I don't think we have anything
And then exactly. And then I ended. But I don't want to get yeah.
Alright, well, let's move on to questions for for NHP, I got it, and then, there was, oh, okay, I messed it up, because they're not pretty. I messed up the material too.
also have a line there. C3 to B3 element there. That would be trigonal,
No, I'm not that good at chemistry. I just know what's happening. I'm not good You're not asking about the suicide. No, no. I'm just I'm working on one and this is kind of
That's what we were just talking about. We were confused when you're supposed to use like certain dots and you're supposed to use the dots.
Guys, I'm coming around to see build structures. So start building some. Okay, I think that one.
Let me try. Let me try and redo this one. How did you do X?
Yeah, you have to have.
So you did the dots.
Yeah.
There were 4 dots.
Yeah, there were 4 dots on.
So we're building CH3C2. Was there a paper? I feel like I need it here. Wait, what's happening?
Okay, some of you guys are getting to the xenon ones and the ones that can't be built because you don't have the color scheme. Choose the appropriate number of holes you need on the little bead. So if you have 5 attachments and a lone pair, you need 6 holes. If you have 4 attachments and lone pairs, you need 4 holes. And just make it work in accordance to the number of things you need. Okay, I'm coming around for checking
Can we just pick a random one? Yeah. So, you have down black, white, and then we'll oh wait, hold on. Is chlorine out? Yes, it is. So yeah, this is chlorine. So you're just going to connect that with right. 1, 2, how many?
So they're like Legos. I know.
Okay, so this is, it's I don't know the actual name. So this is polar. I said it was polar. So there's a CH3 scale. I need to choose AO.
Can you bring that? Can you?
Probably not. Because I think it would just be whatever PDA it is, just so we're not going to go. Another housing. we were to use it to figure out like another neutron system. I mean, this one has four, so it's different. Five.
Oh yeah, the so big in school the day we have the test. They just had noise, they kicked it around the
It's supposed to be like my birthday present for my girlfriend.
H2, I still got two H2s. S is oxygen.
And then we just need to make sure that we we thought in the mornings that so we need black
I think she was talking about this. She said something about this one. And then she was like, oh, you did this. I think she was like, so I think I did this. Yeah. So I need two compasses, which would be yeah, no, that's why I'm so like, it doesn't match up. That's literally some carbon black. Sulfur, yellow. That's black. That's yellow. Hi. Carbon, sulfur, 4. Oh no, it's well, you can use different colors. You just ran
Every time we turn, we have to take it out. I feel every single time we have
I hope we didn't have what? No, they were yeah. Oh God, Kelly. Okay, yeah.
Just build. I don't know what to do. Any color as long as you can justify it. Just right here. Get a black one. Oh my God. Okay, just build.
It's like this.
What is it's a house, it's so wait, I don't know.
Well, it was like yellow and silver.
This one, so it's carbon silver.
Got everyone cleaning up. Everybody still has their H2SE, so hydrogen white, oxygen group is in red. What did we do for FE? We didn't get there yet. No, we did. No, it was an FEF. Oh, I think we just made up. Here's that. Oh, yeah, this was D. What is D? Alright, we're going to do the big ones for the stuff that we want to do. Oh, this one has like 2 ones. I think this one's 4. That one is the first one. Yeah. This one is I have this. Wait, which one? Color means unconditional. Okay. And then that one was CS2 carbon sulfur 2. That one is hydrogen 2.
Alright guys, I need time back from you to deassemble. I will check more tomorrow. Deassemble.
So it has to have double bond, so it has this is so, oh my god, let's do it.
Go in the hole. Come on, back down. Come on. Come on. Alright, and you're back up here in 10. 9. Yeah. Move back to your seats, yeah. 8. 7. 3. 2. We're in slow-mo.
I don't know what you said. So like the very trying to speak
Alright, come back to me. Come come back to me. Very, very bueno. Like, pretty good on your structure. Very bueno. Very, very bueno. Okay, I do what I want. All right. So, my two slackers that are still in the back, guys. They're working on it.
Don't be a slacker.
All right. So, everybody, I want you to, and I know some of you guys think it's to the point where you could build these, but tell me the shape of this. Square planar. Okay, so this is the xenon. This is the xenon F4. Look at your structures on your tables. Some of you guys made it to this point where you're like, okay, it had 6 ligands / lone pairs, so you needed 4 spaces plus 2 dots or 2 holes for the lone pairs. So that looks like a flat square, right? So what does that truly look like? It's kind of supposed to look like this, like a rhombus with a flat square, and there's these huge lone pairs on top and bottom. So I try with the 2D shapes, 3D shapes on the board. But regardless, your arrows or your dipole moments are pointing towards fluorine on all of these accounts, because fluorine is the most what? Electronegative. So you're pulling left, right, up, and down, and it's all the same pull. So you push the electrons out. Yes, so this outside area here is partial negative, partial negative, partial negative, and partial negative. But what's actually happening here is that this fluorine's canceling out this fluorine, and this fluorine's canceling out this fluorine, and this lone pair is canceling out this lone pair. So everybody's going to cancel each other out. So that's nonpolar, right? Then you have the one like this. Anybody pick up on this shape? Yeah. What's this shape?
That is a
So look at the base.
square pyramidal.
Square pyramidal, right? It's not on your sheet, but you can visualize it by looking at it. So which is that one? The xenon with the what? With the oxygen, okay?
And fluorine.
So here, basically it's the same structure. Look up here as I modify. And so you've got xenon with 4 fluorines and oxygen with this little lone pairs, right? And then you have the lone pair hanging off the bottom. But as I connect the dots here, okay, trying to. It just ends up looking like a force barrier, don't it? But overall, do you see that's kind of a pyramid?
Yes.
And there's a lone pair on the bottom. So, is this lone pair being canceled?
No.
So overall,
They're polar.
it's polar because it's not canceling out the other lone pair. So the OX or xenon OF4, is that how it's written?
OF4, yes.
Okay, this would be a polar molecule overall. What's up, Grant?
Let's say on a test or quiz, we have to be able to identify the shape.
I will always give you the sheet. And I'm giving you low end and high end in class, but I usually have some middle region stuff on tests and quizzes.
So you want to just like give us
I won't be like,
you won't name the shape.
no. But what I would expect that you could do is draw it and figure out the shapes by looking at our cheat sheets. Okay? All right, come back up here because we're going to talk about the application of this polarity stuff now, okay? So, I have to skip ahead here. All right, write down this piece of information for me in your notes.
Oh, I got you. When's your birthday again?
First, the very first.
Day after Halloween. My birthday's the day after Halloween. My brother's the day after St. Patrick's Day. My mom's is the day after Cinco de Mayo.
My birthday is May 24th.
Mine's on the first. Mine's January 1st.
You have to remember all this.
We're gonna give you some fun facts about y'all.
Wow.
Can everybody get one of those papers? It's okay. Alright. Squirrel. Right in here. Squirrel. Alright, so as you're writing, I'm gonna quiz you. Ready?
You're ready.
Ready?
I'm top quiz or
Top
just
quiz. I know, I'm just joking. So where have you heard the word enter before in life?
Like won't go into
Okay, no. This enter. Not E-enter. Okay, interview, international, what else? Interstate. Okay, so all of those situations. Okay, I got enough examples. Thank you. All right, so all of those examples you just named off were an interview between two people. Interstates, like an interstate road between two states. Interstates. International, between two nations. Okay. Okay, a number of, yeah. So I'm just saying two because that's the most simplistic view I can make. So the word inter, or the prefix inter, just means between, right? So if I'm talking about intermolecular, put it together for me.
Between molecules.
Right, so we're talking about two molecules, molecule A and molecule B, and we want to know what they're doing between the molecules. And that's simply attraction. This little dashed line that I've drawn here is an attraction. Some things do a fantastic job at attracting other molecules. Some things could care less. What kind of molecules kind of distribute themselves around the room and they don't really interact with other molecules very well? Gases in general. Let's just go gases. I like to ask these and see if you guys know much there. But yeah, gases don't really interact with other gases very well, so a lot of times they kind of distribute themselves around the room and disperse, diffuse. But like ionic compounds, they totally like hanging out with other things. And that's more about the magnetic attractions they have. So we're going to compare inter to intra. Think now about a word that you've heard intra with before.
Introvert.
Introvert, okay.
Oh, no, sorry.
Introvert, that's what Introvert. Anybody else?
Oh, wait, can it be intro?
Intra.
It has to be intro.
Introvert. Guys, we're having a spelling test.
That's what I'm saying. It's like one of those things I just heard for intro.
Okay. Come back to me. Guys. Okay, so I got one good example. I'm good. I don't need any others. So introvert is what most people would think of there, and that's kind of when you're thinking like, I want to hang out with myself. I'm good. I'm happy. I'm not interacting with others. It's more about inside. So in terms of what that means in chemistry, we're talking about inside of a molecule or a formula unit. The word formula unit is just the individual ionic compound. So the word molecule we'll generally be using alongside of covalently bound compounds. So covalent molecules and ionic formula units, which I usually abbreviate as FU. Okay, so. All right. So no.
I just love that.
All right. So continue in a second. Okay. In a second. All right. So these are the ones that are considered the intra, the within forces, the forces that are within a molecule or a formula unit. So write down this. I'll explain what all this means as soon as you write it down. But write down this first, and then we'll kind of tag team on what this means. So basically right now we're talking about how strong attractions are between molecules and within molecules. So we're talking about how strong attractions are within molecules or, in the next slide, between molecules. let you get it down first and then we'll chat.
Wait, can you start like half? Like all the way, just for like a second. All right.
I'm videoing and mine's wrong. They're on the PDFs. Alright, I'm going to scroll back down to this as I start to talk about that section, but I'm going to start talking about the ionic section. Okay, I'm going to scroll back up to the ionic section. I'll come right back down to this. I promise. I promise. You guys get your panties in a bunch for no reason. Okay. Alright, so we're talking about the strength between ions when we're talking about ionic strength. So interparticle attraction, right? But it's still an intramolecular force because it's talking about an individual ionic compound. So if we have to compare the strength of ionic bonds to other ionic bonds, we have to have a system for that. So the system is you have to consider something called the lattice energy. Well, this doesn't mean anything to you yet, but the way we determine the lattice energy or how strongly bound that lattice is we have to look at the charges of the ions. So I'm going to scratch this 3 out and you do the same. This is not how we write aluminum oxide. It doesn't have a 3 in it. But I'm telling you that because I need to tell you now. Look at your periodic table. Look at aluminum. And what charge would aluminum form? As an ion. As an ion. Look for aluminum. A positive what? Come on, be confident.
Am I right?
Okay, if we look over here on my periodic table, pointing to aluminum right there, it has how many valence electrons? 3. Okay, so it's going to form a what charge? Positive 3, because it's going to lose all 3 of those. Okay, so Al is going to have a 3+ charge. Oxygen. Look at oxygen. How many valence electrons does it have? 6. So it's going to form -2, because it would rather gain 2 versus lose 6, right? So it's going to get a -2 charge. So what I'm now going to do is I'm going to do something called charge product, like the product in math, right? What's product mean in math?
Answer to a multiplication.
What? Okay, product means what in math? To a what kind of problem? Multiplication, right? So multiplication problem. So we're going to multiply our 2 charges. What is, and do absolute value for me, okay? What is 3 times 2? 6. Okay, do the same. What's sodium's charge? Sodium's in group 1.
Plus
1 valence electron plus 1, right? What's chlorine's charge? -1 because it's in group 7. So it's going to gain what? 1 electron to form an ion. Okay, so what's 1 times 1? 1. Okay, sodium oxide. Sodium, same one from before, right? So sodium's got a 1+ charge. Oxygen has a 2- charge, as you can see up here in our previous example. What is 1 times 2? 2. So what we can do now is I can say, okay guys, who has a stronger ionic bond? Aluminum oxide, sodium chloride, or sodium oxide? Who has the strongest charge, meaning the highest, and I didn't give you that disclaimer, the highest charge product? Aluminum oxide, okay. So aluminum oxide, because this is its formula, is stronger than who? Give me the next one in line. Sodium oxide, which is stronger than who? Sodium chloride. So we're ordering them based on the strength of their ionic bond. And the strength of the ionic bond is dependent upon what? The charge product, right? Or just the charges in general. Okay, so note to self, if I ever ask you to compare ionic bond to ionic bond, you multiply their charges of the 2 individual ions. Whoever has the bigger charge product, which you can see, nope, that's paintbrush. I want to highlight it. That's highlighter. You can see those charges here, here, and here. That's how you'll determine the strength of an ionic bond. Yes?
So you always do that.
Yeah, it's just because we want the number itself, not the sign. Another question? Say again? So the charge product is what that's called. Okay. And we look at the ionic bond strength that way. Now ionic is slightly different, covalent is slightly different. Ionic bonds are the strongest types of bonds we have, supposedly. Though water can break them apart, it's kind of a weird thing. Covalent bonds, we look at their strength in kind of a different way. That's why I have to compare them kind of in a separate setting. So I'm going to first go down here. So in terms of the type of bonds we can have between two atoms in a covalent bond, they're either single, double, or triple bonds. Single bond, and this is kind of how we'll not really draw them, but we'll recognize the fact of this when we draw them. Single bonds are the long single bonds. Double bonds, as things, and well, let me actually have you guys do something with this. Can you guys just hold the person's hand next to you? Oh, just do it. Just do it. Somebody see somebody? Come here, Anthony, come here. Come on, come on. Okay. All right, so don't look at him. I know, don't look at him. It's okay. Okay. So, right now, make a double bond. Double bond. Okay. Did you guys realize you moved a little closer?
Yes.
All right. Now get your knee in there. All right, double bond. Okay. So we got closer. So as you go from long single bond. Long single bond, double bond. Okay, and then triple bond. Okay.
Makes sense.
So I don't think you'll forget that. Alright, wipe your hands off. You guys got cuties now, sorry. Okay, person next to you.
But I'll do it since you're doing it.
Alright, back to me. I'm reeling you back in. With me, okay. So long single bond, and it's not so strong, but it's a long bond. As the double bond is forming, it's a little stronger because the atoms are getting closer together. And as the triple bond forms, it's even shorter and stronger because the atoms get closer and closer together. So each time the atoms were farther apart, they're closer together, they're closer together. So who's the strongest bond in terms of covalent? Triple bonds. Who's the weakest bonds in terms of covalent? Single. Okay? And these things can happen across many atoms. I'm giving you a simplistic views of just two atoms involved. You could easily imagine this could be 15 atoms involved and have a number of single and double bonds. So that's why we have to recognize there's many atoms involved, and then that all of those atoms have different shapes, which you guys can obviously see now. With me? Thanks. Okay, so now we're going to talk about the Vesper theory with respect to intermolecular forces. All right, so this is the big idea. So a lot of you guys are like, what are we learning this stuff? This is my crazy art one. So write down just a big and bold, intermolecular forces. So you'll notice I didn't say intra, I said what? Intermolecular forces control all physical properties. And I got crazy with the smartboard. You could tell? Oh, I wasn't sure. Look at this.
I think that's awesome.
Okay. So rainbows. I can't get that easily accessible, so I'm going with purple. Okay. So as a quick reminder, what are some physical properties that maybe you remember? Shout them out. Color. What else? Melting point. Freezing point. State of matter. Let's go. Let's go. Woo. What else? That's more for metals. This one's going to be more for our covalent stuff, so I'm going to scratch that for now. Conductivity. Yeah, actually, but I'm not. That doesn't apply right here. Any luster, color. Yeah, those are physical properties. All right, you guys got it. Let me add one more. So melting point, freezing point, state of matter. I'm also going to say solubility. Okay. Oh, did you? My bad. Okay. All right. So here's the scenario. Who wears makeup? Girls. Okay. Okay. So I'm just personal survey. Who's ever? Okay. Back to me. Who's ever gotten Sharpie on their hand? Okay. Who's ever not been able to really get the Sharpie off? Most of us have struggled there. Okay. How have you gotten, or if you've been successful? Raise your hand. Can you tell me a chemically special way that you did it? Not yet. Okay, Olivia? Nail polish remover. Okay, I got nail polish remover. What else? Hand sanitizer. Anybody else? Sunscreen. Okay, so water didn't take it off? Okay, so water, you would be scrubbing your skin cells off for days. But water eventually get off because you're just basically slobbing off skin. But acetone, which is nail polish remover, alcohol, that's in hand sanitizer, and not sure, but I'm sure it's alcohol in sunscreen, all of that mingles with Sharpie marker really, really well. There's different alcohols and all kinds of things, okay? So, there must be a reason that water doesn't interact with Sharpie, but all these other things do. And it's actually the intermolecular forces they have. Makeup, just fun fact, water will just make that mascara just streak on down your face, right? Or just not come up at all, all right? How do some of us who maybe deal with that, how do we get the makeup off? Coconut oil, little face wash of different sorts. Anybody else? Vaseline. Anything else? Okay. You're gonna have to. Okay. All right. So back to me. No, guys. Okay, back to me. So what all this have in common is that they're an oil-based product. Makeup generally is non-polar. You don't just slap some vegetable oil on your face, but you're going to put something that has an oil-based product in it. So, coconut oil works, lotion that has like, any face lotion works, and it's actually moisturizing your face at the same time. So, fun fact, don't even buy the makeup remover, people. It's
that's bad for you. It's bad for you. Well, really?
Well, face lotion a lot of lotions have alcohol in it, which dries out your skin. Face lotion is better for your body.
Wait, so
Okay. I use face lotion where I gotta use it. Yeah. Because it's better for most of your body. Okay. Okay. We're gonna watch our quick video on this. Okay. And I just passed out these items. Good conversations today. Appreciate you. You see this up here? If you did not,
I didn't even realize you put it on our desk. I didn't realize that.
Okay, listen up. Crazy brains. Okay, so we're going to fill out this section on top as this man talks, and I will elaborate by writing on the board. Okay, and I think this will be a good way to introduce it to you, and then we'll finish more of this tomorrow. Okay, Grant, hit the lights for me. Thank you. All right, movie watchers, guys, you're my movie watchers. Guys, you are movie watchers. You got to be quiet, and your cell phone should not be in front of you. You know how that works. Yeah, please.
Forces are the intermolecular forces are the forces in between molecules. In particular, we're talking about the attractive forces. The attractive forces between molecules is really what ends up governing all physical properties. And when I say physical properties, I mean boiling point, melting point, viscosity, surface tension, stuff like that are physical properties. And it's really governed by how strongly these molecules are stuck together. Turns out a lot of these intermolecular forces also affect the way chemicals react, because a lot of these same forces govern the way chemicals come together, and then if you can get them together, you have the possibility of a chemical reaction. We generally cover three basic intermolecular forces that we give three distinct names. The differences are really pretty subtle. It all comes down to the difference of a positive charge and a negative charge. That's really what the attractive force is about. So you have positive and you have negative. The more positive it is, the more negative it is, the stronger the force. This is simply Coulombic attraction. Positive attracts negative. And we have all degrees of this. It's just a matter of how positive and how negative. Most molecules, being neutral species, do not have full positives and full negatives on them. That tends to be the world of ionic molecules. So we're constantly writing partial positive and partial negative. We even have the way we symbolize it on paper, which you should be used to as these partial positive and partial negative charges. Matter of fact, if you can get enough distribution within your molecule to where you have a lot of positive charge on one side and negative charge on the other, you can get what we call a polar molecule. A permanent dipole is a polar molecule. And if you have a permanent dipole, you're going to have a setup within the molecule where you always have partial positive, you always have partial negative. And those are going to get together. That's called dipole-dipole interaction, and that is the strongest interaction you can have within a molecule to another molecule.
Okay, so he does not mean the strongest, actually. He means second strongest, but he's going to repeat that. So you're writing in your chart, polar molecule under dipole-dipole, okay? Polar molecules are what interact with each other through dipole-dipole attraction.
Now we have a subset of that that's actually the strongest version of that. They're even stronger than a regular dipole-dipole. And we call it hydrogen bonding. And it's really because it involves hydrogen being the partial positive part of this molecule. Anytime hydrogen is covalently bound to a very electronegative element, and I'll be specific here, it has to be bound to fluorine, oxygen, or nitrogen. And when it is, it becomes so partial positive, and the oxygen or nitrogen or fluorine becomes so partial negative that you get an even higher amount of attraction. So
All right, so all he said there was hydrogen bonding, which I'm telling you is not a true bond, it's just an attraction. Is when a polar molecule with H bonded to F, H bonded to O, or H bonded to N is involved. So you have to have two molecules with H bonded to F, H bonded to O, or H bonded to N. So I like to say hydrogen bonds are fine. F-O-N, okay? So he's going to say now that they're the strongest, so put under strength, this one's the strongest of them all. S. And then dipole-dipole is the second strongest, so I'm just going to put strong.
go ahead and classify that in its own class. We call it hydrogen bonding, but it's really just dipole-dipole interaction, just up a notch. At the low end of the scale are nonpolar molecules. Now, nonpolar molecules are molecules that have no dipole moment whatsoever. They usually are nonpolar due to symmetry arguments, meaning that whatever you argue pointing one way, there's the opposite wave covered somewhere else on the molecule. So all the symmetry wipes out the polarity of the molecule. A good example of this is carbon tetrachloride. Carbon tetrachloride has 4 very polar carbon-chlorine bonds, but they all nullify each other as far as distribution of charge. So it's a nonpolar molecule. However, it will attract another carbon tetrachloride molecule. They do stick. It is a liquid. So there's...
Okay, so he said now, symmetry, now I'm going to wrap this up for the last minute. He said that London dispersion forces are forces that are found between nonpolar molecules. So remember, it's molecules, so I'm going to put S's on these, because it's between molecules. It's the weakest of them all, and they're generally nonpolar simply because of symmetry. We've got like a good tetrahedron or a linear one, but it's the weakest of them all. We will draw these more tomorrow. What I want from you is that you are starting PS 7-8. Give me a good 50%. Okay? Problem set 7-8. We'll finish this tomorrow. It is a combined problem set. It's not 2 separate problem sets. It's combined. Problem set 7-8, because it's all kind of bonding together.